Hi everyone, welcome back. So in this video, I'm going to talk about polyprotic acids. So far, we've focused mainly on monoprotic acids. So what exactly are polyprotic acids? Well, they contain two or more ionizable protons. Remember, acids are proton donors, so if you have a polyprotic acid, as the name suggests, it can donate two or more protons. And each of these protons ionizes in successive steps. Each with its own Ka value. Let's look at sulfuric acid, H2SO3. And when you work with polyprotic acids, once again, just ionize one proton at a time. So donate one proton to water. Water's acting as a base, so the conjugate acid of water is the hydronium ion. And then you end up with hydrogen sulfite as the conjugate base of sulfuric acid. And this ionization step has a Ka, and we're going to label it 1, of 1.6 times 10 to the negative second. This is a weak acid, so it makes sense that even the first ionization step is less than 1. Then hydrogen sulfite can lose its second proton. So once again, donates one proton. There's your one hydronium ion here. And then the conjugate base is sulfite. And the Ka for the second step is 6.4 times 10 to the negative 8th. So significantly lower than the first ionization step. So Ka2 is less than Ka1. Why do you think that is? Now think about it. Opposites are attracted to each other. So the first proton that ionizes, that leaves the molecule, separates from a neutral molecule. The second proton must ionize from a negatively charged ion, an anion. So therefore, it's held more tightly. Remember, protons have a positive charge. So trying to leave a negative charge, which it's attracted to, is so much harder. I like to think of it of kids going off to college. So when my first kid goes off to college, I'm sure it's going to be so hard for me, right? But when my second kid goes off to college, then I won't have any kids home, and that's going to be even harder for me to become an empty nester then, right? And so that's what I like to think of when it comes to these polyprotic acids and their successive ionization steps. You know, the Ka values will get smaller and smaller because it's harder to let go of that proton as you're increasing this negative charge. So we're going to work an example together, actually a couple of examples. I'll work a problem in this video with you, but in the next video I'll do another one as well, just to make sure you feel comfortable with it. But I just wanted to write a side note here to what we've been covering. And I'll cover this in a later chapter as well, but I wanted to include it now since it's obviously relevant. You've seen me talk about how do you know X is small enough to ignore, right? Like ignore X, then you don't have to do the quadratic, but there are times where you can't. And so what's the trick to knowing when you can and when you can't? You want to be able to determine that quickly, right? So the first thing you look at is the initial concentration. The initial concentration needs to be not too dilute. So we're thinking an initial concentration greater than to the 10th place or the 100th place in molarity. In addition, the equilibrium constant must be small. There must not be a huge drive for the forward reaction. So K is equal to some number X times 10 to the negative 5th, negative 6. When you have those orders of magnitude and that small of a K value, it's not going to proceed in the forward direction, so X won't change too much. But basically, the take-home message here, so you can quickly check to see if you can ignore X or not, the initial concentration should be 10 to the second to 10 to the third times greater. And this is for both concentrations. If you have two reactants with two initial concentrations, you want to check it for both. So the initial concentration should be 10 to the second to 10 to the third times greater than K in order for you to ignore X and not have to go through the quadratic formula if that's what you have. If it's a quadratic or if it's a polynomial, you won't have to solve that polynomial by method of successive approximation. So I just wanted to include that side note here in this video, since you're working lots of these problems and you want to find ways to save yourself some time if possible. So there you go. But let's continue on our conversation of polyprotic acids. Here are some common examples of polyprotic acids you come across with in your daily lives, like citric acid, ascorbic acid, and you can see their successive ionization equilibrium constants. They obviously get smaller. It's harder to lose the second and even the third proton even more. So generally, the formation of hydronium ions in the first step inhibits the formation of additional hydronium ions in the second step. And it's due to what principle? Right, due to Le Chatelier's principle. We've discussed this in previous videos already. It's why we're able to ignore the autoionization of water, right? That it doesn't really contribute significantly to the hydronium ion concentration because its equilibrium is suppressed by the ionization of the acid. So therefore, we treat most polyprotic acids as if the first step were the only step. And in the next video, I will work an example problem of that. But in this video, I wanted to work an exception to that rule. I always believe in kind of showing the exceptions so you understand how to work through them. And so we have to consider both ionization steps if we're working with dilute sulfuric acid. Now, sulfuric acid is one of the strong acids, right? H2SO4, but it also has a second ionization step with a significant equilibrium constant that is great enough that it will contribute to the hydronium ion concentration increasing. And you'll see that in a second here. Now, this question's asking us to find the pH of a 0.0100 molar sulfuric acid solution. And so this is the concentration we are working with here, 0.0100 molar. So let's go ahead and write down If you're in my course and I gave you the skeleton notes already, just to make note that the concentration originally written down was 0.1 molar, but we're working with a dilute solution, so now we're looking at 0.0100 molar. So I wanted to highlight that, check that in your notes. All right, so once again, when you work with polyprotic acids, just donate 1 proton at a time. Remember that first proton, since this is a strong acid, this is not in equilibrium here. That arrow is going straight forward. And we're left with the conjugate acid of water, because water is accepting the proton, and that's the hydronium ion. And the conjugate base of sulfuric acid is HSO4 here, hydrogen sulfate, as shown here. So once again, just focus on 1 proton at a time. Don't try to donate both protons at the same time. Now, I want to make a note here that this is a strong acid, and if you try to find the Ka value of a strong acid, you're not going to have any luck because the Ka value is huge, right? And it goes to completion. Ka values are given for weak acids only. So just a tip is that if you're doing an assessment and you're working with an acid, and let's say I don't provide the Ka value, and you're sitting there like, how am I supposed to do the rice table if there's no Ka value provided? Kind of backtrack yourself and say, wait a second, is this a strong acid? If it is, then maybe I'm overthinking this a little bit. So just little words of wisdom, just make sure that if you have a strong acid, there's no need for a Ka value, there's no need for a rice table, right? Because we know that the concentration of the sulfuric acid is equal to the concentration of the hydronium ions in this first step. It's a 1-to-1 ratio, by the way. Okay, so we're just doing 1 step at a time. So 1-to-1 ratio. So the hydronium ion concentration is equal to 0.0100 molar. In addition, your hydrogen sulfate concentration is also 0.0100 molar, right? Because this completely dissociates into both, okay? So let's write down the second step. So this was the first step, first ionization. Now let's look at the second. So hydrogen sulfate plus water. Now this one's going to have a Ka less than 1. So we are doing a rice table. It is in equilibrium. It's going to donate a proton to water. Water is acting as a base. It goes from H2O to H3O+. Conjugate acid of water, once again, is the hydronium ion. And I know I'm redundant when I say that over and over again, but if you also talk yourself through these reactions, then it will stick better, right? Try to teach yourself this, and say it out loud. Conjugate acid of water is the hydronium ion. All right, so therefore, if hydrogen sulfate loses its proton, it ends up losing that positive charge. It goes to from a negative to a -2, and that's sulfate 2-. You would have seen this. This is very common polyatomic ion. And if we were to look up the Ka value, it is equal to 0.012. So since the Ka value, the second ionization step for sulfuric acid, is actually quite significant, that means that the equilibrium is going to go forward quite a bit. We're going to get a significant contribution of hydronium ions, so that we do need to take into account. We have to do this second step, this rice table here. All right, let's start filling in that rice table. Remember, we have to fill in what's happening initially. Initially, we have 0.0100 molar of the hydrogen sulfate. And we see that from the first step here. When sulfuric acid completely dissociates, it gives us 0.0100 molar of the hydrogen sulfate. And then also it gives us 0.0100 molar of the hydronium ion, and then nothing initially for the sulfate. And then as it changes over time, it's -1x, +1x, +1x. Remember, we don't include water. That's why I keep marking it out. And then at equilibrium, hydrogen sulfate was be 0.0100 minus X. And this one is 0.0100 plus X. And then 0 plus 1X is X. Our goal is to find the pH. Right? That's our goal here. We need to find the pH. You can find the pH from the hydronium ion concentration at equilibrium. So not only do we need to find X here, we need to take that and add that to 0.0100 to figure out the total hydronium ion concentration once sulfuric acid has completely dissociated here, and then undergoing that second ionization step there. All right, so to do that, we got to set it up to the Ka expression. Always products over reactants. So the hydronium ion concentration times the sulfate over hydrogen sulfate. Whoopsie, that's a -1. And that is equal to an X times 0.0100 plus X over 0.0100 minus X equals to 0.012. Now this is where you're like, can I ignore X? That would make this math so much easier. But unfortunately, let's go back to the rules, that basically the initial concentration should be 10 to the second or 10 to the third times greater than K. And unfortunately, it's not. If you take 0.01 over 0.012, it's essentially 1. So X is not small enough to ignore. This is too dilute of a solution to do that. All right, so therefore, I'm going to do some of the math here. You can follow with me, or you can pause the video and get yourself into the quadratic to make sure that you feel comfortable with the work. Kind of multiplying the numerator through. I'm going to multiply both sides by the 0.01 minus X. I'm going to combine like terms and then set one side equal to 0 to get me into the quadratic form. And then set it up to the quadratic to find the two solutions for X. So remember, it's -b plus or minus the square root of b squared minus 4ac over 2a. And the two solutions you should get are -0.027 or X is equal to 0.0045. Now remember, you can never have a negative concentration. So one of these solutions is always bogus, and in this case, it's the -0.027, because just can't have a negative concentration at equilibrium, not going to happen. So X is equal to 0.0045. So let's continue on. The hydronium ion concentration at equilibrium is equal to 0.0100 plus 0.0045. And that is equal to 0.0145 molar. The pH is equal to the negative log of the hydronium ion concentration. And therefore, you should get an answer of 1.84. What's in your beaker? a dilute sulfuric acid solution, you definitely expect a pH less than 7, and indeed we do, especially for something that's a strong acid. So in summary, if you have a dilute sulfuric acid solution, remember sulfuric acid is a polyprotic acid. The first step is just the strong acid ionization where the concentration is equal to the hydronium ion concentration as well as the conjugate base. You have to do the second step for the sulfuric acid because its Ka value is pretty significant. We are going to get a change in X so that we can find the equilibrium concentration after the second proton starts ionizing. We had to solve for X, we had to use the quadratic, so make sure you practice that, you feel comfortable with this, with the math of it, the algebra, and then plug it in to figure out what that hydronium ion concentration is once that second step has reached its dynamic equilibrium. And then the pH is the negative log of that hydronium ion concentration, which is 1.84. So once again, this is kind of the exception to the rule. Now in the next video, I will also work how to calculate the pH of a weak polyprotic acid, where you really only need to take into account the first step. So stay tuned. Thank you guys for watching, and I will see you next time.